Deep in the vast expanse of space, far beyond the reach of our most powerful telescopes, lie silent witnesses to the birth and evolution of the cosmos itself. These aren't planets or stars as we know them, they're galactic fossils, ancient relics that have been quietly recording the passage of time for billions of years, long before Earth even existed. Picture this, a celestial body so old, its surface holds scars from the earliest moments of the universe, a natural archive of cosmic history written not in words, but in stardust and radiation. These fossils don't tick or talk like the clocks we're familiar with. Instead, they tell time through the slow decay of elements, the fading glow of long-dead stars, and the subtle shifts in their chemical makeup. They're the universe's way of keeping a diary, one that stretches back further than our minds can fathom. What makes these galactic fossils so extraordinary isn't just their age, it's what they reveal about the very nature of time. Unlike human-made clocks, which measure seconds and minutes in neat, predictable increments, these cosmic timekeepers operate on a scale that defies imagination. A single moment in their timeline could span millions of our years. They challenge everything we think we know about how time works, forcing us to reconsider whether it's as constant as we believe. Imagine holding a rock that formed when the Milky Way was just a swirling cloud of gas, or studying a dying star whose light has traveled across space for longer than Earth has existed. These aren't just scientific curiosities, they're keys to unlocking the universe's deepest secrets, and that's exactly what we're about to explore. Together, we'll journey through the cosmos to uncover how these ancient celestial bodies preserve the past, from the remnants of supernova that scattered the building blocks of life across the galaxy, to the interstellar dust clouds that still carry echoes of the Big Bang. We'll see how scientists decode their hidden messages, piecing together a story that spans nearly 14 billion years. This isn't just a tale of distant stars and cold, lifeless rocks. It's a story about us, about how we fit into the grand timeline of the universe. By the end, you'll never look at the night sky the same way again. So let's begin. The cosmos is waiting, and its oldest storytellers are ready to speak. Galactic fossils are the universe's ancient librarians, holding records of cosmic events so old they predate our solar system by billions of years. Take white dwarfs, for example, the dense, cooling cores of dead stars. These fading embers are like celestial time capsules, their outer layers slowly crystallizing over eons into a bizarre form of metallic ice. By studying their composition, scientists can trace the nuclear reactions that powered their parent stars, revealing what the cosmos was like when those stars were born. Then there are neutron stars, the collapsed remnants of supernova explosions so violent they crushed atoms into a sea of pure neutrons. Their rapid spins act like cosmic metronomes, ticking with precision for millions of years, while their surfaces bear scars from collisions with other ancient objects, each dent a timestamp from deep space's violent past. But perhaps the most astonishing fossil isn't an object at all, it's the faint afterglow of the Big Bang itself, known as the cosmic microwave background radiation. This whisper of energy fills every corner of the universe, a snapshot of what space looked like when it was just 380,000 years old. It's like finding a baby picture of reality, frozen in microwaves that have been traveling uninterrupted for over 13 billion years. Unlike Earth's fossils, which are locked in rock, these cosmic relics are dynamic. They change in ways that let us measure time itself on a scale no human clock could ever match. The heavy elements in a white dwarf's core decay at a rate so slow it makes geological time seem rushed, while the gradual cooling of neutron stars unfolds over intervals longer than human civilization has existed. What ties these objects together is their ability to preserve information against the erasing tide of time. Just as tree rings tell us about Earth's climate history, the layers of a white dwarf's atmosphere contain isotopes that act as breadcrumbs leading back to the early universe. Even the distribution of galaxies across the sky, a fossilized imprint of primordial density fluctuations, holds clues about how gravity sculpted the cosmos over billions of years. These aren't just curiosities for astronomers, they're vital pieces in the puzzle of how everything we know came to be, and the most humbling part, we're only beginning to decipher their stories. Every new observation peels back another layer, revealing just how much these silent sentinels have witnessed and how much they still have to teach us. White dwarfs are like the universe's most meticulous historians, preserving stellar secrets in their ultra-dense cores long after their parent stars have faded away. Imagine a sphere the size of Earth but containing nearly the mass of our Sun, so compact that a single teaspoon of its material would weigh as much as an elephant. This extreme density isn't just a curiosity, it's what makes white dwarfs such perfect cosmic clocks. As these stellar remnants gradually cool over billions of years, they do so with remarkable predictability, their temperature dropping at rates physicists can calculate with astonishing precision. Think of them as celestial coals from a long-extinguished fire, radiating heat into space at a pace that allows astronomers to determine exactly how long they've been cooling. But these objects aren't just simple thermometers. Their surfaces are layered like the pages of a history book, each stratum telling a different chapter of their star's life. When white dwarfs first form, they're so hot that their outer layers churn violently, mixing elements like oxygen, carbon, and helium in a swirling stellar soup. Over time, heavier elements sink while lighter ones rise, creating distinct chemical bands that scientists can read like tree rings. What makes this particularly fascinating is that these elements aren't native to the white dwarf. They're the ashes of nuclear fusion from its previous life as a star. By analyzing these element patterns, researchers can reconstruct what that star was burning before its death, effectively carbon dating stellar evolution itself. Perhaps the most extraordinary feature of white dwarfs is their role as cosmic alchemists. As they cool, some undergo a transformation so strange it sounds like science fiction. Their carbon-rich interiors crystallize into a form of metallic ice, creating what's essentially a diamond the size of a planet. This process happens over timescales that dwarf human civilization, with some white dwarfs taking up to 100 billion years to fully solidify. That's longer than the current age of the universe. This slow-motion metamorphosis provides physicists with a natural laboratory to study quantum mechanics under conditions impossible to recreate on Earth. The way heat moves through these crystallizing cores reveals fundamental truths about how matter behaves under extreme pressure, offering clues about the ultimate fate of all stars, including our own Sun. What truly sets white dwarfs apart as timekeepers is their stubborn resistance to change. Unlike active stars that burn through their fuel unpredictably or black holes that warp space beyond recognition, white dwarfs fade with mathematical regularity. Their steadfast cooling curves have become one of astronomy's most trusted yardsticks for measuring cosmic time, helping scientists calibrate the ages of star clusters and even refine estimates for when the first stars blinked into existence. Every white dwarf we observe is both a relic and a Rosetta Stone, a silent witness to stellar lives long past, and a key to understanding the grand chronology of our universe. Their patient glow across the eons reminds us that sometimes the best way to measure time isn't with ticking hands, but with the gradual dimming of ancient starlight. While white dwarfs measure time through their slow cooling, neutron stars, especially pulsars, keep cosmic time with a precision that would make even the most advanced atomic clocks on Earth seem crude by comparison. Born from the violent deaths of massive stars in supernova explosions, these city-sized remnants pack more mass than our Sun into a sphere just 12 miles across. The physics at play here is mind-bending gravity so intense that protons and electrons fuse into neutrons, creating a substance so dense that a sugar cube-sized piece would weigh as much as Mount Everest. But what truly sets pulsars apart is their spin. Some rotate hundreds of times per second, sending beams of radiation sweeping across space like lighthouse beacons with a regularity that rivals the finest human-made timekeeping devices. The consistency of these cosmic metronomes is staggering. Take the famous PSRB 1937+21, a pulsar in the constellation Vulpecula that spins precisely 642 times per second. Observations spanning nearly 40 years reveal its rotation varies by less than 1 second every 250 million years, a level of stability that makes our leap-second adjustments to atomic clocks look like constant tinkering. This isn't just a curiosity, it's a tool. Astronomers use these predictable pulses to navigate the Milky Way, much like sailors once used stars, by tracking how a pulsar's signal changes as Earth moves through space. The rhythmic flashes create a celestial GPS system, helping spacecraft orient themselves in the void. Pulsars also serve as extraordinary laboratories for testing Einstein's theory of general relativity. When a pulsar orbits another dense object, like the case of the Hulse-Taylor binary system, the extreme gravity warps spacetime in ways that subtly alter the timing of its pulses. Over decades, these minute deviations have provided some of the strongest evidence for gravitational waves, exactly as Einstein predicted. It's as if the universe provided us with perfectly synchronized clocks placed in its most extreme environments, just so we could watch how gravity bends the rules of time itself. Beyond their precision, pulsars preserve history in their very structure. The oldest known pulsars, called millisecond pulsars, have been spun up to incredible speeds by stealing matter from companion stars, a process that can take billions of years. Their current rotation rates are like cosmic fingerprints, revealing details about their violent pasts and the dynamic interactions that shaped them. Some even bear scars from ancient collisions, their surfaces permanently dented by impacts with asteroids or other stellar remnants during the chaos of the early universe. Every pulse carries information not just about the present, but about events so distant in time that Earth didn't exist when they occurred. What makes these spinning sentinels truly humbling is their potential longevity. While white dwarfs will eventually cool into dark crystals and black holes evaporate over incomprehensible timescales, a pulsar's spin could persist for trillions of years, outliving every star in the current universe. Their steady ticks may one day be the only signs of activity in a cold, dark cosmos, the last timekeepers in an era when all other lights have gone out. For now, they remain both our most precise cosmic clocks and our most reliable witnesses to the universe's deepest mysteries, their rhythmic flashes writing the time across the sky in beams of radio waves and X-rays. Supernova remnants are the universe's most dramatic time capsules, preserving the exact moment a star's life ended in a cataclysmic explosion. Picture an expanding cloud of gas and debris stretching dozens of light-years across space, still moving outward at thousands of kilometers per second, not as random chaos, but as a perfectly preserved record of a single violent instant billions of years ago. What makes these remnants so valuable to scientists isn't just their spectacular appearance, it's how they function as cosmic stopwatches. By measuring how far the shockwaves have traveled and calculating their expansion speed, astronomers can rewind the tape to pinpoint exactly when the supernova occurred. It's like finding a shattered stopwatch in space, its hands frozen at the moment of detonation. The most famous example is the Crab Nebula, the aftermath of a star that Chinese astronomers observed exploding in the year 1054. Today, 11 centuries later, we can still see its debris expanding at nearly 1,500 kilometers per second. But not all remnants are so cooperative. Some reveal their ages through more subtle clues. The elements forged in the supernova's intense heat, like titanium, nickel, and gold, form distinct patterns in the expanding gas. These heavy elements act like chemical timestamps, decaying at known rates that let scientists determine when they were created. It's forensic astronomy at its finest, with each remnant offering multiple independent ways to verify its age. What's truly remarkable is how these remnants bridge time on cosmic scales. The youngest, like Cassiopeia A, exploded just 350 years ago, recent enough that we can watch their shockwaves interact with interstellar material in real time. Others, like the Vela supernova remnant, are ancient by human standards at around 11,000 years old, yet still infantile compared to the universe's 13.8 billion-year history. This range gives astronomers snapshots of stellar death at different evolutionary stages, much like having photographs of a person at every age. Beyond their chronological value, these remnants are cosmic recycling centers. The heavy elements they scatter: oxygen for our lungs, calcium for our bones, iron for our blood, were forged in their explosions. Every atom in your body that isn't hydrogen likely passed through one of these stellar furnaces. This makes supernova remnants not just timekeepers, but the very reason complex life exists. Their violent death seeded the galaxy with the ingredients for planets and living organisms, connecting our existence directly to these ancient explosions. Perhaps most astonishing is how these remnants continue evolving long after their initial detonation. The shockwaves plow through interstellar space, compressing gas clouds that may one day collapse into new stars that will eventually explode and continue the cycle. In this way, supernova remnants aren't just relics of the past, they're active participants in shaping the future of the cosmos. Their timelines don't end with the explosion, but extend forward through the generations of stars and planets they'll help create, making them both historians and prophets of galactic evolution. Among all the galactic fossils we've explored, none holds a candle to the cosmic microwave background, the oldest light in existence, a whisper from the universe's very first chapters. This faint glow, invisible to human eyes but detectable by sensitive telescopes, is the afterglow of the Big Bang itself, stretched and cooled over 13.8 billion years into microwave radiation that now permeates every cubic centimeter of space. What makes it extraordinary isn't just its age, it's that this light was emitted when the universe was a mere 380,000 years old, a cosmic toddler compared to today. Back then, the cosmos was a scorching plasma soup, so dense that light couldn't travel freely. But as the universe expanded and cooled, atoms formed, and suddenly, photons could escape, creating the first sunrise in cosmic history. That light has been traveling ever since, carrying with it a pristine snapshot of the infant universe, frozen in time like a mosquito trapped in amber. The patterns in this ancient light are anything but random. Tiny fluctuations in temperature variations as small as 1 part in 100,000 reveal regions where matter was slightly denser or sparser than average. These imperfections are the seeds of everything we see today. The slightly denser patches, amplified by gravity over eons, became the galaxies and galaxy clusters we observe now. It's as if we're looking at the blueprint for the cosmos, with every filament of the cosmic web, every void between galaxies, encoded in those faint microwaves. Scientists have mapped these variations with stunning precision using satellites like the Planck Observatory, creating all-sky images that are essentially baby pictures of reality. But the CMB isn't just a relic. It's an active tool for measuring the universe's vital statistics. By analyzing its patterns, cosmologists have determined the universe's age down to an astonishing precision of about 20 million years, a rounding error on cosmic timescales. They've measured the amounts of ordinary matter, and dark energy with percentages that would make a lab chemist envious. The CMB even holds clues about the universe's shape, confirming it's flat to within a margin of error of just 0.4%. These aren't abstract numbers, they're the foundational parameters that govern how galaxies form, how fast space expands, and ultimately, how long the cosmos might endure. What's perhaps most mind-bending is that this radiation isn't just something we observe, it's something we're immersed in. The static on an old analog television. About 1% of that snow comes from CMB photons hitting the antenna. Every time you warm leftovers in a microwave oven, a tiny fraction of the heating comes from the same light that once filled the newborn universe. It's a humbling thought. The afterglow of creation is literally everywhere, a constant background hum to existence that most of us never notice. Future civilizations, trillions of years from now, might look up to a sky devoid of galaxies as we know them. But even then, the CMB will persist, faded but detectable, the last visible relic of a time when everything began. Unlike other cosmic fossils that tell us about specific events or objects, the CMB is the ultimate panoramic archive. It doesn't just record a star's death or a galaxy's birth, it captures the initial conditions of reality itself, a Rosetta Stone written in the language of temperature variations and polarization patterns. And we're still learning to read it. Recent studies of the CMB's polarization hint at primordial gravitational waves, ripples from the universe's exponential expansion in its first split second of existence. Others are searching for subtle distortions that might reveal collisions with other universes in the multiverse. With each technological leap, we peel back another layer, listening ever more closely to an echo that has traveled across 99.99% of cosmic history, an echo that still has secrets to share. Drifting between the stars, invisible to the naked eye, are trillions of microscopic timekeepers, grains of interstellar dust so small you could fit thousands on the head of a pin. Yet within these tiny particles lies a record of cosmic events stretching back to before our solar system formed. Each speck is a frozen moment in galactic history, carrying isotopes forged in the hearts of dying stars. Unlike the grand celestial fossils we've explored, white dwarfs, pulsars, and supernova remnants, these dust grains tell time on an atomic scale. Their isotopic clocks tick away silently as radioactive elements decay at rates so consistent they rival the precision of laboratory instruments. Take a single grain of stardust that formed in the aftermath of a supernova explosion 5 billion years ago. Locked within its crystal structure are atoms of aluminum-26, an isotope with a half-life of 717,000 years. By measuring how much of this aluminum has decayed into magnesium-26, scientists can calculate exactly when that grain was born in the stellar explosion. It's like finding an hourglass buried in space with the sand still falling at a known rate. Other isotopes, like iron-60 with its 2.6 million year half-life, serve as chronometers for different cosmic events, allowing researchers to build a layered timeline of galactic history from these microscopic archives. What's astonishing is how these grains preserve their stories despite eons of drifting through hostile space. Their outer layers may erode from radiation or collisions, but their crystalline cores remain pristine, protecting their atomic clocks like a time capsule within a time capsule. Some even contain pre-solar material, dust that predates our sun, giving us direct samples of the building blocks of our solar system. When scientists analyze these grains under electron microscopes, they're not just studying dust. They're holding pieces of stars that died billions of years before Earth existed. The real magic happens when these atomic clocks are cross-referenced with other cosmic fossils. A dust grain with a particular isotopic signature might match the age of a nearby supernova remnant, confirming when that stellar explosion occurred. Others show spikes in certain elements that align with periods of intense star formation in our galaxy's spiral arms. Together, they form a web of chronological data points, transforming random dust into a coordinated network of cosmic stopwatches. Perhaps most remarkably, some of this interstellar dust eventually finds its way to Earth. Every year, our planet sweeps up about 40,000 tons of extraterrestrial material, much of it microscopic dust grains from distant stars. Hidden among these particles are the same isotopic timekeepers that float between the stars, meaning the history of the galaxy is quite literally falling on our heads. The next time you see dust floating in a sunbeam, consider this: somewhere in that mundane household dust might be atoms that witnessed the birth of our Milky Way, silently marking time until science learned to read their stories. These unassuming specks challenge our perception of what a clock can be. They remind us that time isn't just measured in ticks and tocks, but in the slow transformation of matter itself. As we develop new ways to collect and analyze interstellar dust, from high-altitude balloon experiments to future space missions, we're essentially building a microscope for cosmic time, one that lets us peer deeper into our galaxy's past than ever before. The universe's history isn't just written in light years and supernovae, it's encoded in particles so small they could float on a breeze, yet carry the weight of billions of years. Globular clusters are the universe's oldest neighborhoods, tightly packed cities of stars that have remained virtually unchanged since the cosmos was young. Imagine a million suns crammed into a space so small that the night sky from a planet within one would blaze with stars brighter than our full moon. These spherical swarms orbit galaxies like ours like bees around a hive, their stars bound together by gravity for over 13 billion years. What makes them extraordinary isn't just their age, it's that nearly all their stars were born at the same time, frozen in a single snapshot of the early universe. While galaxies like the Milky Way continuously form new stars, globular clusters are cosmic time capsules, their stellar populations preserving the chemical fingerprints of the universe's youth. The stars in these clusters are the ultimate historians. Unlike stars in the galactic disk, which recycle material through generations of stellar births and deaths, globular cluster stars formed from pristine gas that had never been enriched by supernova. Their atmospheres contain barely any heavy elements, just hydrogen and helium with traces of lithium, making them the closest things we have to the universe's original stellar recipe. By studying their light with spectrographs, astronomers can read these chemical signatures like pages in a cosmic ledger, revealing how elements were distributed when the first galaxies were assembling. Some clusters even show multiple generations of stars, with younger members subtly enriched by the ashes of their elders, a fossil record of how star formation changed over billions of years. Perhaps the most astonishing thing about globular clusters is how they've survived. In the chaotic environment of a young galaxy, where collisions and tidal forces routinely tear star clusters apart, these ancient structures have endured. Their incredible density, up to 1,000 stars per cubic light year near their cores, acts as a shield against disruption. Stars whip around their common center of gravity at hundreds of kilometers per second, creating a gravitational fortress that has withstood the universe's turbulence since before Earth existed. Some clusters show scars from close encounters with galactic centers or other clusters, their outer stars stripped away like leaves in a storm, yet their cores remain intact, still ticking like clocks wound at the dawn of time. These clusters don't just tell us about the past, they help calibrate the present. Because all their stars formed simultaneously, astronomers can use them to test theories of stellar aging. The hottest, most massive stars in a cluster burn out first, leaving behind cooler, redder stars whose properties reveal the cluster's age with precision. This makes globular clusters cosmic yardsticks for measuring distances across the universe. By comparing their apparent brightness to their known intrinsic brightness, scientists can calculate how far away they and their host galaxies are. Some, like Omega Centauri, are so bright they're visible to the naked eye from Earth, their light a direct link to an era when the universe was less than 1 billion years old. What's truly humbling is realizing these clusters may outlast everything else we know. Long after the Milky Way collides with Andromeda in 4 billion years, long after all star formation ceases in the distant future, globular clusters will likely still orbit whatever galaxy remains, their stars shining faintly but persistently. They're not just relics of the past, they're messengers to the far future, carrying the story of the universe's beginnings into epochs we can scarcely imagine. Every time we study one, we're not just looking back in time, we're touching something that might well be among the last structures standing when all other lights have gone out. Dark matter doesn't glow, reflect, or absorb light. It doesn't interact with the electromagnetic force at all, yet its gravitational fingerprints are everywhere. This invisible scaffolding makes up about 85% of the universe's matter, weaving an unseen web that galaxies cling to like dew on a spider's silk. Without it, the cosmos as we know it wouldn't exist. But here's the fascinating part. Dark matter isn't just passively filling space, it's actively shaping the timeline of cosmic evolution. Every galaxy, every cluster, even the vast voids between them bear the imprint of dark matter's silent influence over billions of years. To understand how dark matter records time, picture a cosmic construction site. When the universe was young, slight density variations in the dark matter, web imperfections left over from the Big Bang acted like blueprints for future structures. Gravity amplified these tiny fluctuations, pulling dark matter into dense clumps that ordinary matter would later follow, forming stars and galaxies. The distribution of galaxies we see today isn't random. It's a frozen moment in this gradual assembly, a snapshot of dark matter's patient work. By studying how galaxies are arranged across space, astronomers can essentially rewind the tape, reconstructing how dark matter's gravitational pull orchestrated the universe's large-scale structure over billions of years. One of the most compelling pieces of evidence for dark matter's timeline comes from something called gravitational lensing. When light from distant galaxies passes through massive galaxy clusters, the cluster's gravity, dominated by dark matter, bends the light like a lens. The amount of bending reveals how much dark matter is present and how it's distributed. By analyzing these distorted images, scientists can create three-dimensional maps of dark matter's invisible architecture, tracing its growth from the early universe to today. Some of these maps show dark matter filaments stretching across millions of light-years cosmic highways, along which galaxies have traveled since the dawn of time. But dark matter's story isn't just about structure, it's also about timing. The rate at which galaxy clusters formed, the speed at which galaxies spin, even the temperature of gas in interstellar space, all these phenomena depend on when and how dark matter accumulated. For example, galaxies in the early universe rotate faster than they should based on their visible mass alone. The only explanation: they're embedded in massive halos of dark matter that began forming long before the first stars ignited. These halos aren't static, they evolve, merging and growing as the universe expands, their changing dynamics encoding a record of cosmic history. Perhaps the most tantalizing clue dark matter offers is its connection to the universe's accelerating expansion. By measuring how dark matter's distribution has changed over cosmic time, scientists can test whether dark energy, the mysterious force driving the acceleration, has always behaved the same way. Some theories suggest dark matter particles might interact with each other in ways that subtly alter their clustering over eons. If true, these interactions could rewrite our understanding of the universe's fate. What makes dark matter such a powerful timekeeper is its persistence. Unlike stars that burn out or galaxies that collide and morph, dark matter endures, its gravitational influence continuing uninterrupted across the ages. Every fluctuation in its distribution, every filament in its cosmic web, tells part of a story that began before the first atoms formed, a story we're only just learning to read. As detection methods improve, from underground particle experiments to space telescopes mapping its gravitational effects, we inch closer to decoding dark matter's hidden chronicle. It's a reminder that sometimes the most revealing histories aren't written in light, but in the silent tug of gravity across the void. At the chaotic hearts of galaxies, supermassive black holes lurk like cosmic archivists, their very existence telling the story of unimaginable violence across billions of years. These gravitational monsters don't just consume matter, they grow through cataclysmic mergers, absorbing entire stars, gas clouds, and even other black holes in a process so energetic it ripples space-time itself. Every time two galaxies collide, their central black holes eventually spiral together in a deadly dance, creating gravitational waves that echo across the universe. The final product, a single, more massive black hole, carries permanent scars from this brutal history. Its mass becomes a ledger of everything it's consumed, while its spin reveals the angle and ferocity of past collisions, like a bullet's rifling marks preserving details of the gun that fired it. Take the black hole at the center of our own Milky Way, Sagittarius, a star. While it's relatively quiet now, weighing in at 4 million times the Sun's mass, its size hints at a violent past. Astronomers suspect it grew to its current stature through multiple mergers with smaller black holes during our galaxy's early days, when chaotic collisions were commonplace. But Sagittarius, a star, is modest compared to true cosmic titans like the black hole in galaxy M87, a behemoth 6.5 billion times more massive than our Sun. That staggering mass suggests an insatiable appetite spanning eons, with countless mergers fueling its growth. What makes these black holes such precise timekeepers is how they preserve merger details in their fundamental properties. When two black holes collide, their combined spin isn't random, it depends on the angle of impact and the original spins of the merging pair. Picture two spinning tops crashing together. The resulting motion encodes information about the collision itself. By measuring a black hole's spin using the intense radiation from its accretion disk or the bending of light around its event horizon, scientists can reconstruct merger events that occurred when Earth was still molten rock. Some black holes spin near the maximum possible rate, their event horizons whipping around at nearly light speed, a telltale sign of multiple mergers where angular momentum piled up like a cosmic inheritance. The most dramatic evidence of these ancient mergers comes from gravitational wave detections by observatories like LIGO and Virgo. When two black holes spiral together, they create ripples in spacetime that propagate across the universe at light speed. The frequency and amplitude of these waves reveal the black hole's masses before merger, while the signal's decay rate shows how quickly they coalesced. In 2015, LIGO made history by detecting waves from two black holes 30 times the Sun's mass colliding 1.3 billion years ago. Since then, dozens of mergers have been recorded, each a snapshot of black hole evolution at different cosmic epochs. But supermassive black holes tell more than just their own stories. They're traces of galactic evolution. Every major galaxy merger leaves its mark on the central black hole's growth, which in turn affects the entire galaxy's development. When black holes feed, they launch powerful jets that can heat surrounding gas, shutting down star formation across thousands of light years. This feedback mechanism means a black hole's merger history is written not just in its mass and spin, but in the very structure of its host galaxy, the distribution of stars, the shape of spiral arms, even the presence of satellite galaxies. Perhaps the most astonishing implication is that black holes may preserve information from universes that predate our own. Some theoretical models suggest certain black holes could be primordial, formed not from dying stars, but in the extreme conditions just after the Big Bang. If these ancient black holes exist and later merged with stellar or supermassive ones, their unique signatures might still be detectable in the gravitational wave background, a faint hum of vibrations from countless mergers across cosmic time. As detection methods improve from next-generation gravitational wave observatories to precision measurements of black hole shadows, we're gaining the ability to read these cosmic scars with ever greater clarity. Each supermassive black hole is more than a gravity well. It's a palimpsest of violence, its growth rings recording the mergers that shaped our universe, layer by layer, collision by collision. Their silent presence reminds us that the cosmos doesn't just move forward, it also remembers. The Milky Way isn't just a collection of stars, it's a sprawling cosmic museum, each celestial object holding clues to our galaxy's turbulent past. Galactic archaeologists don't need shovels or brushes. Their tools are telescopes and spectrographs, dissecting starlight to uncover stories written in the language of chemistry and motion. Every star in our galaxy carries a hidden label, a unique chemical signature imprinted at birth. Stars that form together in the same stellar nursery share nearly identical compositions, like siblings with matching DNA. Over billions of years, these stars may drift apart, scattered by the Milky Way's rotation or gravitational tugs from passing gas clouds, but their chemical fingerprints remain unchanged. By cataloging these signatures across hundreds of thousands of stars, scientists can trace their origins, reconstructing migration patterns that reveal how our galaxy grew, merged, and evolved. This stellar detective work hinges on a phenomenon called nucleosynthesis, the process by which stars forge heavier elements in their cores. When massive stars explode as supernova, they seed their surroundings with these newly minted elements. The next generation of stars forming from this enriched material carries a distinct chemical marker, like a timestamp of the galactic environment when they were born. Older stars, like those in the Milky Way's halo, contain barely any elements heavier than hydrogen and helium, a telltale sign they formed before many supernovae had occurred. Younger stars, like our Sun, are richer in metals, proving they were born from gas recycled through multiple stellar life cycles. It's as if the galaxy keeps a running ledger of its chemical evolution, with each stellar generation adding a new entry. But galactic archaeology goes beyond chemistry. It also reads the motions of stars like pages in a history book. The Milky Way's disk, halo, and bulge each host stars with distinct orbits, relics of different formation eras. Some stars move in tight, circular paths, suggesting they've lived quiet lives in the galactic suburbs. Others follow wild, elongated trajectories, often a giveaway that they were stolen from smaller galaxies the Milky Way cannibalized long ago. One famous example is Gaia Enceladus, the ghost of a dwarf galaxy that collided with our own nearly 10 billion years ago. Its stars still move as a coherent group, their unusual orbits and chemical makeup betraying their foreign origins. These stellar immigrants are cosmic artifacts, evidence of the violent mergers that shaped our galaxy's adolescence. The European Space Agency's Gaia mission has revolutionized this field, mapping the positions, motions, and compositions of over 1 billion stars with unprecedented precision. This vast dataset lets astronomers play galactic historian, identifying stellar families and reconstructing events from epochs when Earth didn't exist. One surprising discovery: the Milky Way's disk shows ripples and wrinkles, distortions likely caused by past encounters with satellite galaxies. These gravitational echoes persist for billions of years, frozen in the motions of stars like grooves in a vinyl record. What makes galactic archaeology so powerful is its ability to peer beyond the limits of traditional astronomy. While telescopes can't directly observe the Milky Way's past, the stars remember. Their compositions and orbits form a multilayered archive, chronicling everything from ancient collisions to periods of intense star formation. And just as archaeologists on Earth use pottery shards to reconstruct lost civilizations, astronomers use stellar data to piece together our galaxy's epic saga, one that's still being written with every new generation of stars. Imagine a star reaching the end of its life, not with a bang, but with a slow unraveling its outer layers, drifting away while its core collapses into a dense white dwarf. Now picture this stellar corpse surrounded by a bizarre graveyard, shattered planetary fragments, vaporized asteroids, and the dusty remains of entire worlds that once thrived in orbit. These aren't hypothetical scenarios, they're real systems we've observed, where the chemical fingerprints of obliterated planets linger in the atmospheres of their dead stars. White dwarfs, typically pristine spheres of hydrogen and helium, sometimes show unexpected traces of heavier elements like iron, silicon, and even oxygen elements that shouldn't exist on their surfaces unless they've recently consumed solid material. It's as if the star has turned into a cosmic archaeologist, preserving the ruins of its own planetary system in its atmosphere. Take GD 392, a white dwarf located about 160 light-years from Earth. Spectroscopic analysis revealed its atmosphere is contaminated with elements that closely match the composition of Earth's crust, an astonishing clue that this star likely devoured a rocky planet similar to ours. The amounts detected suggest the destroyed world was at least as massive as Vesta, the second largest asteroid in our solar system. Even more intriguing is WD 1145+017, where astronomers found evidence of a water-rich asteroid belt once orbiting the star, a ghostly reminder that distant solar systems may have hosted oceans and possibly even habitable worlds before their violent demise. The presence of these elements isn't just incidental, it's a smoking gun. Heavy elements sink rapidly in a white dwarf's intense gravity, meaning any metals we detect must have been deposited recently, astronomically speaking, within the last million years or so. This gives us a snapshot of planetary destruction in action. But how do planets end up falling into their dead stars? The process begins when a sun-like star exhausts its nuclear fuel and swells into a red giant, engulfing or destabilizing any nearby planets. What survives this phase faces an even grimmer fate. As the star sheds its outer layers and collapses into a white dwarf, its gravitational pull becomes erratic, sending surviving planets and asteroids into chaotic orbits. Tidal forces rip some apart, creating disks of debris that spiral inward like water circling a drain. Others collide in violent impacts, producing clouds of dust that eventually rain down onto the white dwarf surface. The result is a forensic goldmine, a stellar crime scene where the chemical composition of the debris reveals exactly what kinds of planets once existed there. What makes these systems so valuable is their ability to preserve planetary diversity from different cosmic eras. While we can study exoplanets around living stars using transit methods or direct imaging, those techniques mostly reveal contemporary worlds. White dwarf pollution, on the other hand, lets us analyze planets that formed billions of years ago, some from the Milky Way's infancy. The ratios of elements like magnesium to iron or carbon to oxygen act as cosmic DNA, telling us whether these ancient worlds had metallic cores, thick silicate mantles, or even carbon-rich surfaces unlike anything in our solar system. Some white dwarfs show excess infrared radiation from circumstellar dust, disks, the pulverized remains of what were once mighty gas giants or icy moons. Perhaps the most sobering realization is that our solar system will likely suffer the same fate. In about 5 billion years, the Sun will expand past Earth's orbit, possibly vaporizing our planet before settling into its own white dwarf phase. The surviving outer planets and asteroids may then plunge into the dead Sun, leaving behind a chemical record for any distant observers to decipher. This cyclical nature of stellar life and death means that today's exoplanet systems are tomorrow's white dwarf artifacts, and yesterday's alien worlds are now the elements we detect in these ancient stellar remnants. By studying these cosmic graveyards, we're not just learning about other solar systems, we're glimpsing the ultimate destiny of our own celestial neighborhood. Every polluted white dwarf is both a tombstone and a time capsule, its atmospheric chemistry whispering secrets of planets lost to time. And as our telescopes grow more sensitive, we'll uncover even more of these fossilized systems, piecing together a galactic history written not in stone, but in stardust and spectral lines. Stretching across the night sky like ethereal brushstrokes, stellar streams tell a story of destruction and rebirth on a galactic scale. These shimmering rivers of stars aren't random. They're the shredded remains of smaller galaxies and star clusters torn apart by our Milky Way's immense gravity. Picture a cosmic spiderweb, with each silken strand representing stars once bound together in dwarf galaxies, now slowly unraveling across hundreds of thousands of light years. The most famous example, the Sagittarius Stream, forms a delicate loop around our galaxy, the last gasp of a dwarf galaxy that's been steadily consumed over the past 4 billion years. Its stars move in unison like a school of fish, their shared motion betraying their common origin despite being scattered across 1/3 of the visible sky. What makes these streams such precise timekeepers is their predictable behavior. As a small galaxy falls into the Milky Way's gravitational pull, tidal forces stretch it like taffy, creating leading and trailing arms of stars that continue orbiting long after their parent galaxy's core has been digested. By measuring how far these arms have unwound and calculating their orbital speed, astronomers can pinpoint exactly when the destruction began, like rewinding a cosmic movie to see the moment of impact. Some streams, like the relatively young Orphan Stream, show minimal dispersal, suggesting their progenitor was disrupted just a few 100 million years ago. Others, like the ancient Casito Stream, have stars so widely dispersed they're barely recognizable as a group, marking mergers from when the Milky Way was in its violent youth. The chemical composition of these stars adds another layer to the story. Stars born together in the same galactic nursery share distinct elemental fingerprints, allowing astronomers to match dispersed stream stars to their original families. The Phoenix Stream, for example, contains stars with unusually high levels of R-process elements, heavy metals typically forged in neutron star collisions. This chemical signature suggests its parent galaxy experienced a rare flurry of these catastrophic events before being torn apart. Other streams show peculiar abundances of alpha elements like oxygen and magnesium, clues about the star formation rates in their original homes before the Milky Way consumed them. Modern sky surveys have revealed these stellar rivers are far more common than we once thought. The Gaia spacecraft alone has identified nearly 60 separate streams crisscrossing our galactic neighborhood, each representing a different act of cosmic cannibalism. Some are long and thin, tracing graceful arcs around the Milky Way, the remnants of globular clusters slowly dissolving into the galactic halo. Others form broad, diffuse bands, the shredded corpses of dwarf galaxies that once rivaled the large Magellanic Cloud in size. Together, they form a complex web of mergers, a timeline of the Milky Way's growth written in starlight. Perhaps most astonishing is how these streams help map the invisible. As stellar rivers pass through regions rich in dark matter, their gravity subtly distorts the stream's shapes, creating kinks and gaps that reveal the dark matter's distribution. The GD1 stream, stretching across 30 degrees of sky, shows a peculiar gap and offshoot that some scientists believe was caused by a dense clump of dark matter punching through it like a bullet through smoke. These interactions provide some of the clearest evidence yet for dark matter's lumpy, hierarchical structure throughout our galaxy. Looking forward, stellar streams promise to reveal even more about our galaxy's past and future. Upcoming telescopes like the Vera Rubin Observatory will likely discover hundreds more of these fossilized mergers, helping reconstruct the Milky Way's assembly history in unprecedented detail. Some streams may even lead us to still intact dwarf galaxies, waiting to be consumed, future chapters in our galaxy's ongoing story of growth through destruction. Every new stream mapped is another piece of the puzzle, showing us that galaxies aren't static islands in space, but dynamic structures forever changed by their violent encounters. The stars we see tonight as isolated points of light may once have belonged to entirely different galaxies, their streaming paths connecting us to cosmic events older than Earth itself. Determining the universe's age isn't about checking a single cosmic clock. It's about assembling a vast, interlocking network of celestial timepieces, each ticking at its own pace across different eras of cosmic history. Picture a detective solving a mystery by comparing multiple eyewitness accounts, where white dwarfs serve as stellar stopwatches, globular clusters act as ancient hourglasses, and the cosmic microwave background provides the ultimate timestamp from the universe's infancy. Each of these galactic fossils tells time in its own language, yet together they converge on a startlingly precise number, 13.8 billion years. Take white dwarfs first, the cooling embers of dead stars. Their predictable temperature decline allows astronomers to calculate how long they've been radiating heat into space. The oldest known white dwarfs in globular clusters have been cooling for nearly 13 billion years, setting a firm lower limit on the universe's age. But these stellar remnants don't work alone. Globular clusters, those dense swarms of stars orbiting galactic halos, provide independent verification. Because all stars in a cluster form simultaneously, astronomers can estimate their age by observing which stars have already exhausted their nuclear fuel and evolved off the main sequence. The most ancient clusters, like M92, contain stars nearly as old as the universe itself, their faint light a direct link to cosmic dawn. Then there's the cosmic microwave background, the afterglow of the Big Bang. This faint microwave whisper contains temperature fluctuations that reveal the universe's exact state at 380,000 years old. By measuring how these patterns stretch across the sky and applying our understanding of cosmic expansion, scientists have pinned down the universe's age to within just 20 million years, a blink in 13.8 billion. What's remarkable is how these disparate methods agree. When white dwarf cooling curves, globular cluster ages, and CMB measurements all point to the same time frame, it gives us extraordinary confidence in our cosmic chronology. Yet the story isn't without its wrinkles. Earlier measurements using the Hubble constant the rate of the universe's expansion sometimes clashed with age estimates from galactic fossils. Faster expansion rates suggested a younger universe than the oldest stars appeared to be, creating what astronomers called the age crisis. This tension forced scientists to refine their models, eventually leading to the discovery of dark energy and the realization that the universe's expansion is accelerating. Today, precise measurements of distant supernova and baryon acoustic oscillations help calibrate the expansion rate, bringing all cosmic clocks into harmony. The real power of this multi-method approach becomes clear when we find anomalies. Certain ultra-faint dwarf galaxies contain stars that initially appeared older than the universe itself, an impossibility that led to revised calculations of stellar evolution models. Similarly, discrepancies in early CMB measurements hinted at new physics, driving upgrades to satellite instrumentation. These challenges don't undermine our timeline, they refine it, pushing our understanding to greater precision. Like detectives cross-examining witnesses, astronomers weigh conflicting evidence to arrive at a more complete truth. What emerges from this cosmic detective work is more than just a number, it's a narrative. 13.8 billion years marks the time since the Big Bang, but also frames everything we know about cosmic evolution. It tells us when the first stars ignited, how long galaxies took to assemble, and even places limits on when life could have arisen. Each independent clock, whether based on radioactive decay in meteorites, the spin down of pulsars, or the clustering of galaxies, adds another layer of certainty to this grand timescale. And as our tools improve, from 30-meter telescopes on the ground to space-based gravitational wave observatories, we'll likely uncover even more ways to read time's passage written in the stars. Einstein's theory of relativity isn't just abstract mathematics, it's written into the fabric of the cosmos, and galactic fossils are some of its most dramatic proofreaders. Near incredibly dense objects like neutron stars, time doesn't flow at the steady pace we're used to on Earth. Instead, it warps and stretches, ticking slower in the crushing grip of extreme gravity. This phenomenon, called time dilation, transforms these celestial remnants into natural laboratories for testing relativity's most mind-bending predictions. Take pulsars, those rapidly spinning neutron stars we've come to rely on as cosmic metronomes. Their beams of radiation sweep past Earth with such regularity that tiny deviations in their pulse timing reveal profound truths about spacetime. When a pulsar orbits another massive object, like a white dwarf or black hole, its pulses arrive at Earth slightly delayed when the star is on the far side of its orbit, deeper in its companion's gravitational well. This isn't because the pulsar is actually slowing down. It's because time itself is passing more slowly in that intense gravitational field. The effect matches Einstein's equations with precision down to fractions of a percent, turning these binary systems into some of the most stringent tests of general relativity ever conducted. Perhaps the most striking example is the double pulsar system Pulsar J0737-3039, where two neutron stars orbit each other every 2.4 hours. The stronger gravitational field of the more massive pulsar slows time near its surface so dramatically that clocks there tick about 38 microseconds slower per day than those on its lighter companion. That might sound negligible, but over years of observation, this tiny discrepancy has confirmed relativistic predictions with astonishing accuracy. The system's orbital decay caused by energy lost through gravitational waves also aligns perfectly with Einstein's calculations, providing dual validation of relativity from a single cosmic source. But time dilation isn't just a curiosity, it has real observational consequences. When astronomers study X-ray emissions from matter spiraling into a neutron star's surface, they detect subtle shifts in the wavelengths of light as photons struggle to climb out of the star's gravitational pull. This gravitational redshift, another relativistic effect, alters the apparent chemical signatures of elements in the star's atmosphere, creating patterns that wouldn't exist in weaker gravity. By comparing these distorted spectra to laboratory measurements, physicists can essentially weigh the neutron star, determining its mass with precision that would be impossible without accounting for relativity's time-warping effects. What makes these galactic fossils so invaluable is their ability to push relativity to its limits. Near a neutron star's surface, gravity is so intense that space-time curvature approaches levels impossible to recreate in any Earth-based experiment. The fact that pulsar timing, gravitational redshift, and orbital dynamics all behave exactly as relativity predicts under these extreme conditions is perhaps the theory's greatest triumph. It's one thing for equations to work on paper. It's another to see them hold up where gravity is 100 billion times stronger than on Earth. These natural experiments are still yielding new insights. Recent observations of pulsars near the Milky Way's central supermassive black hole are testing whether relativity's predictions hold in environments where multiple extreme gravitational effects overlap. Others are searching for minute deviations that might hint at new physics beyond Einstein's theory, clues about quantum gravity or hidden dimensions that could only manifest where space-time is stretched to its breaking point. Every pulsar that ticks in sync with relativity's beat reinforces our understanding of the universe's deepest workings, while any that stutter might point the way to revolutions yet to come. In the end, these galactic fossils do more than just tell time. They reveal time's very nature, showing us a universe far stranger and more wondrous than our everyday experience suggests. They prove that time isn't an absolute backdrop to existence, but a dynamic, malleable dimension woven inseparably into the cosmic tapestry. And with every precise pulse from these spinning relics, we're reminded that some of science's most profound truths are written not in textbooks, but in the silent, patient language of the stars. Deep within the atmospheres of ancient stars, atomic clocks have been quietly ticking since the dawn of time, not with gears and springs, but with the steady decay of radioactive elements forged in the hearts of long-dead stars. These chemical chronometers rely on elements like uranium-238 and thorium-232, isotopes with half-lives comparable to the age of the universe itself. When the first generations of massive stars exploded as supernova, they scattered these freshly synthesized elements across the cosmos like cosmic confetti. Later generations of stars incorporated these radioactive seeds into their very fabric, their isotopic ratios becoming frozen moments in galactic history. Take the star He 1523-0901, one of the oldest known in our galaxy. Spectroscopic analysis revealed it contains measurable amounts of both uranium and thorium elements that decay at precisely known rates. By comparing their current ratio to the initial ratio expected from supernova nucleosynthesis, astronomers calculated this star formed approximately 13.2 billion years ago, making it nearly as old as the universe itself. This technique works because uranium decays faster than thorium over billions of years. Their ratio shifts predictably, like an hourglass where one grain represents uranium atoms turning into lead, while another represents thorium's slower transformation. But uranium and thorium aren't the only elements acting as cosmic clocks. The rare earth element europium holds secrets too. It's primarily produced in neutron star mergers rather than ordinary supernova. When astronomers find stars with unusually high europium abundances, they're essentially seeing timestamps from ancient cosmic collisions. One such star, SMSS J20032-1142, contains europium levels suggesting its material was enriched by a neutron star merger that occurred just 100 million years after the Big Bang. That makes it a living relic from an era when the first heavy elements were being forged in the most violent events imaginable. What makes these chemical clocks so reliable is how they cross-validate each other. The decay of potassium-40 into argon-40 provides an independent check on uranium-thorium dates, while the ratio of iron-60 to nickel-60, both formed in supernova, offers yet another timeline. When multiple isotopic systems in the same star agree, it's like having several synchronized watches all confirming the same cosmic time. This multi-method approach has revealed that some of the Milky Way's oldest stars formed within just a few 100 million years of the first supernova, their chemical compositions preserving a record of the universe's earliest element factories. Perhaps the most astonishing aspect of nucleosynthesis dating is how it connects us directly to these primordial events. Every uranium atom in Earth's crust, every thorium atom powering deep-sea vents, was created in the same stellar explosions that enriched those ancient stars. The difference is that while Earth's radioactive elements have been recycled through geological processes, the atmospheres of metal-poor stars preserve these elements in nearly pristine condition. Studying them is like comparing a weathered ancient coin found in an archaeological dig to one perfectly preserved in a time capsule. Both tell the same story, but one retains far more detail. As telescopes grow more powerful, they're revealing even rarer isotopic combinations that act as stopwatches for specific cosmic events. The ratio of plutonium-244 to uranium-238, for example, can distinguish material produced in rare supernova from that made in more common stellar explosions. Other isotopes like curium-247, with its 156 million-year half-life, provide shorter-term clocks for dating more recent nucleosynthesis. Together, they form a layered chronology of element formation, allowing scientists to reconstruct not just when stars formed, but what kinds of stellar deaths preceded them. This chemical archaeology is rewriting our understanding of the early universe. Stars once thought to be nearly primordial are now revealing subtle signatures of even earlier generations, ghost stars that lived fast, died young, and left behind only their elemental fingerprints in subsequent stellar generations. With each new isotopic ratio measured, we're peeling back another layer of cosmic history, reading a story written not in ink, but in the slow decay of atomic nuclei across the depths of time. Even the most precise galactic fossils come with their own set of cosmic uncertainties, gaps in our knowledge, that remind us how much we still have to learn about the universe's timeline. Take white dwarfs, those stellar embers we rely on as natural clocks. While their cooling rates follow predictable patterns, interpreting their ages requires near-perfect models of stellar physics. A tiny miscalculation in how heat moves through their crystallizing cores could throw off age estimates by hundreds of millions of years. And some white dwarfs show unexpected temperature plateaus, periods where their cooling seems to stall, possibly due to unseen chemical separation in their interiors. These anomalies don't invalidate their use as timekeepers, but they do highlight how even the most reliable cosmic clocks need occasional recalibration. The challenges multiply when we study relics that leave only indirect traces like dark matter. We can map its gravitational influence on galaxy rotations and cosmic web structures, but without directly detecting its particles, we're forced to make assumptions about how it behaved in the early universe. Did it clump together faster than ordinary matter? Did it interact with itself in ways that altered galaxy formation? These unanswered questions mean dark matter's timeline comes with wider error bars than we'd like. Even the cosmic microwave background, our gold standard for dating the universe, has uncertainties. Its pristine snapshot of the early cosmos still requires interpretation through theoretical filters that might not capture the full picture. Then there's the problem of missing pages in the cosmic archive. Many galactic fossils only preserve certain epochs, leaving gaps in the timeline. Supernova remnants, for instance, are brilliant markers of stellar deaths, but their visible debris dissipates after a few 100,000 years, a blink in cosmic terms. We're left studying the handful of recent explosions in our galactic neighborhood and extrapolating their behavior to ancient events we can no longer observe directly. Similarly, the oldest stars in globular clusters formed from gas already enriched by earlier generations of stars that left no surviving traces. It's like trying to reconstruct a family tree when all the earliest ancestors have vanished without photographs. Perhaps the most humbling limitation is the sheer scale of time we're dealing with. When measuring events billions of years apart, even small percentage errors translate to vast uncertainties. A 1% error in dating the universe's age spans nearly 140 million years longer than all of human evolution, and some processes, like the formation of the first stars, leave no direct fossils at all. We see their influence in later generations of stars and in the faint glow of reionization. But the pioneers themselves remain hidden in the cosmic dark ages, their light too feeble to ever reach our telescopes. Yet these limitations aren't failures, they're invitations to dig deeper. Each uncertainty drives new observations and refinements to our models. The tension between different dating methods, like early Hubble constant measurements conflicting with stellar ages, famously led to the discovery of dark energy. Today, discrepancies in white dwarf cooling rates are prompting physicists to revisit how materials behave under extreme pressures, while anomalies in globular cluster ages are refining our understanding of stellar nucleosynthesis. The gaps in our knowledge aren't empty, they're filled with questions that push astronomy forward. What emerges from these challenges isn't a weaker understanding of cosmic time, but a richer one. By acknowledging where our tools fall short, we avoid the trap of false precision and remain open to surprises. When future telescopes detect gravitational waves from neutron star mergers older than any we've seen, or when new particle experiments finally identify dark matter, they'll slot into this evolving timeline, not as disruptions, but as the next chapters in an epic we're still learning to read. The universe's history isn't a finished book, it's a living manuscript with galactic fossils as our most faithful, if occasionally cryptic, narrators. The next decade will unveil the universe's deepest secrets like never before, thanks to a new generation of telescopes and detectors designed to study galactic fossils with unprecedented clarity. At the forefront is the James Webb Space Telescope, already transforming our view of cosmic history with its infrared eyes. Unlike Hubble, which primarily observes visible light, Webb peers through cosmic dust to study the first stars and galaxies, objects so ancient their light has stretched into infrared wavelengths over billions of years. Recent observations of galaxy clusters like SMACS 0723 reveal structures forming just 300 million years after the Big Bang, a period once thought inaccessible. Webb's spectroscopic tools dissect the chemical makeup of these primordial objects, detecting traces of early supernova and even potential population 3 stars, the universe's first stellar generation, made purely of hydrogen and helium. These observations don't just add to our timeline, they rewrite entire chapters of cosmic evolution. Equally revolutionary is the Vera Rubin Observatory, set to begin its legacy survey of space and time in 2025. This ground-based telescope will image the entire southern sky every few nights for a decade, creating the most detailed time-lapse of the universe ever made. Rubin's wide-field camera will capture subtle changes in galactic fossils, dimming white dwarfs, flaring neutron stars, and the slow unwinding of stellar streams, with a precision that lets astronomers track their evolution in near real time. Its most exciting potential lies in discovering entirely new classes of relics, rogue planets ejected from ancient solar systems, orphaned stars from long-digested dwarf galaxies, or even primordial black holes left over from the Big Bang. Rubin won't just observe these objects, it will map their motions across millions of years, turning static snapshots into a dynamic cosmic film. But the future of galactic archaeology isn't just about light. Gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, will listen for ripples in spacetime from mergers of supermassive black holes, events so powerful they shake the fabric of the universe. When LISA launches in the 2030s, it could detect collisions from the cosmic dawn, revealing how the first black holes grew to billions of solar masses so quickly. These waves carry information no light-based telescope can see, like the spins and masses of black holes that merged before galaxies fully formed. Combined with traditional observations, they'll create a multidimensional picture of cosmic history, where we don't just see the past but feel its gravitational echoes. Spectroscopy is also leaping forward. Next-generation instruments like the Andes spectrograph for the extremely large telescope will analyze starlight with such precision they can detect isotopes in exoplanet atmospheres that were forged in ancient supernova. Imagine identifying the radioactive decay products of aluminum-26 in a distant white dwarf's debris disk, a smoking gun for stellar nucleosynthesis events that seeded life's building blocks. Other projects like the Cosmic Microwave Background Stage 4 experiment will map the Big Bang's afterglow with 50 times the resolution of current telescopes, potentially uncovering primordial gravitational waves or evidence of other universes. What ties these advancements together is their ability to cross-validate each other. Webb might spot a galaxy from the universe's first billion years, Rubin could track its descendants through cosmic time, and LISA might catch the gravitational waves from its central black hole merging with another. This interconnected approach, combining light, gravity, and chemistry, will transform galactic fossils from isolated curiosities into pieces of a unified cosmic narrative. The relics we study tomorrow won't just be older or fainter. They'll tell richer stories, revealing not just when events happened, but how they shaped everything that followed. The most thrilling prospect, discovering fossils we don't even know to look for yet. Just as the Hubble Deep Field revealed thousands of unknown galaxies in a patch of sky thought to be empty, these new tools will inevitably uncover phenomena that challenge our understanding of time itself. Whether it's a pulsar spinning slower than physics allows, a star with impossible elemental abundances, or a gravitational wave signal that doesn't match any known source, these anomalies will push us toward new questions, and perhaps toward rewriting cosmic history once again. The universe's clocks have been ticking for billions of years, but only now are we developing the tools to truly listen to their rhythm. The way we decipher Earth's ancient past has striking parallels with how astronomers read the universe's history. Just as geologists study rock layers to understand our planet's evolution, astrophysicists examine the chemical composition and structure of white dwarfs, neutron stars, and interstellar dust. Both methods rely on nature's meticulous record, keeping whether it's radioactive isotopes trapped in zircon crystals or aluminum-26 decaying in stardust grains. The same principles apply whether you're dating a 4-billion-year-old Earth rock or a 13-billion-year-old star. Time leaves its signature in the very fabric of matter itself. Consider how Earth's geological timescale was built. By examining sediment layers in the Grand Canyon, scientists can trace hundreds of millions of years of planetary history, with each stratum preserving fossils and minerals from its era. Galactic archaeology works similarly when analyzing the Milky Way's stellar populations. Stars in the galaxy's halo are like bedrock, ancient and relatively unchanged, while younger disk stars resemble topsoil, continually churned by galactic dynamics. The orbital motions and chemical abundances of these stars create a stratigraphic column spanning cosmic epochs rather than geological periods. The tools of measurement also share remarkable similarities. Geologists use uranium lead dating to determine a rock's age by measuring how much uranium-238 has decayed into lead. Astronomers apply nearly identical techniques to stars, tracking the decay of uranium-238 and thorium-232 in stellar atmospheres. Both fields even face parallel challenges. Just as metamorphic rocks can reset their radioactive clocks under intense heat and pressure, stars can mix their interiors and obscure their original chemical signatures. Perhaps the most profound connection lies in how both records preserve catastrophic events. Earth's Cretaceous Paleogene boundary layer holds iridium from an asteroid impact that wiped out the dinosaurs. Similarly, stars with unusual europium concentrations bear witness to neutron star mergers that occurred billions of years ago. These chemical spikes act as cosmic equivalents of fossil extinction layers, marking when the universe's most violent events altered the course of galactic evolution. A single white dwarf polluted with planetary debris can tell us about an entire solar system's demise, much like how a single ash layer in Greenland's ice cores documents a massive volcanic eruption that changed Earth's climate. This interdisciplinary perspective reveals something fundamental about nature's methods. Whether on planetary or cosmic scales, the universe documents its history through the same physical processes: radioactive decay, chemical differentiation, and the accumulation of layered evidence. Understanding Earth's geological record helps us interpret galactic fossils and vice versa. When geologists study how zircon crystals trap uranium atoms, they're essentially working with the same principles astronomers use to date stars. The main difference is scale. Where Earth's time span is measured in billions of years, cosmic clocks operate across tens of billions. The parallels extend to how both fields deal with missing data. Geologists face unconformities, gaps in the rock record caused by erosion, just as astronomers grapple with the cosmic dark ages before the first stars formed. Both sciences have developed creative solutions, using multiple dating methods and cross-referencing different lines of evidence. Just as volcanic ash layers help correlate rock sequences across continents, the cosmic microwave background serves as a universal reference point for aligning different galactic timelines. This convergence of Earth and space science isn't just academic, it's reshaping how we search for life's origins. By comparing how organic molecules became trapped in ancient Earth minerals with how complex molecules form in interstellar clouds, we're tracing the universal pathways that lead from simple chemistry to biology. The same radioactive isotopes that date rocks also seeded planetary systems with the heat needed for liquid water and geologic activity. In this light, galactic fossils aren't just timekeepers, they're pieces of a story that connects the formation of heavy elements in dying stars to the very conditions that made our existence possible. What emerges is a humbling realization: the same forces that sculpted Earth's mountains and canyons also shaped the galaxies. Time writes its chronicle in atomic nuclei, whether buried deep in planetary crusts or scattered across light years of interstellar space. By learning to read both records, we're not just studying separate histories, we're uncovering the single, grand narrative of a universe that preserves its past with astonishing fidelity across all scales of existence. Standing beneath a night sky strewn with galactic fossils, we're confronted with a perspective so vast it redefines what time even means. These celestial relics don't just record billions of years, they force us to grapple with durations that dwarf all human history combined. Consider that the light from some white dwarfs began its journey when Earth's most complex life forms were single-celled organisms, or that the gravitational waves from ancient neutron star mergers have been traveling through space since before multicellular life existed. This isn't merely scientific trivia, it's a fundamental challenge to how we perceive our place in the cosmic story. The humbling truth is that human civilization occupies less than a blink in this grand chronology. All our empires, discoveries, and personal struggles unfold within a sliver of time so narrow it wouldn't even register on the timeline of a cooling white dwarf. Yet these same fossils that diminish our temporal significance also connect us to something magnificent. We're made of atoms forged in those very stars we now study. The calcium in our bones, the iron in our blood, even the gold in our jewelry were all created in stellar explosions and neutron star collisions recorded by these galactic timekeepers. We're not just observers of cosmic history, we're its living continuation. This duality of feeling both insignificant and deeply connected sparks profound philosophical questions. If the universe operates on timescales we can barely comprehend, what does that mean for concepts like purpose or legacy? The pulsar that will outlive our sun by trillions of years doesn't care about human achievements, yet its very existence made those achievements possible. These contradictions invite us to reconsider what truly matters when measured against the cosmic clock. Perhaps meaning isn't found in duration, but in our capacity to understand and appreciate the universe that created us. What makes galactic fossils uniquely powerful is how they collapse this immense timescale into something tangible. When astronomers analyze the uranium to thorium ratio in an ancient star, they're not just calculating numbers, they're touching a clock wound at the dawn of time. The cosmic microwave background isn't merely data, it's a direct encounter with the universe's first light. These experiences trigger what psychologists call the overview effect, that cognitive shift astronauts report when seeing Earth from space, but expanded to cosmic dimensions. The fossils become mirrors reflecting our temporal smallness and our extraordinary privilege as conscious witnesses to cosmic history. This perspective shift has practical implications too. Understanding deep time changes how we approach problems like climate change or nuclear waste storage challenges that require thinking beyond individual lifespans or even civilizations. The same radioactive elements we use to date stars also power our reactors, linking our brief moment of technological civilization to processes that began before the solar system formed. Galactic fossils teach us that we're neither the first nor the last chapter in this story. We're transitional beings, capable of both destroying our world and preserving it for future epochs. Ultimately, these celestial timekeepers offer a paradoxical gift. They show us our fleeting nature while revealing our cosmic ancestry. The same supernova that seeded the galaxy with life's building blocks also created the white dwarfs we now study to measure time. We're the universe becoming aware of itself, using the remnants of its violent youth to ponder its origins and destiny. In this light, galactic fossils aren't just scientific objects, they're bridges between the inhuman vastness of cosmic time and the intimate human experience of wondering where we belong in it all. Their greatest lesson might be this: that understanding our smallness in time and space isn't diminishing, but strangely liberating. Among the countless stars dotting our galaxy, HD 140283 stands apart, not just for its age, but for the cosmic puzzle it presented. Nicknamed Methuselah after the biblical figure known for his longevity, this faint star in the constellation Libra initially appeared to be older than the universe itself. When early measurements suggested an age of around 16 billion years, nearly 3 billion years older than the cosmos, it sent shockwaves through the astronomy community. How could a star exist before the universe began? The contradiction wasn't just a minor discrepancy. It threatened to upend our fundamental understanding of cosmic chronology. The key to unraveling this mystery lay in the star's composition and motion. Methuselah belongs to a rare population called metal-poor stars, meaning it contains vanishingly small amounts of elements heavier than hydrogen and helium. This chemical fingerprint marks it as a relic from the universe's first stellar generation, born from nearly pristine gas untouched by previous supernova. Astronomers determined its age by analyzing the star's brightness, temperature, and subtle shifts in its light caused by elements like oxygen and iron. But early estimates relied on incomplete data about its distance, a critical factor in stellar aging models. When the Hubble Space Telescope precisely measured Methuselah's parallax in 2013, it revealed the star was slightly closer and brighter than assumed, adjusting its age downward to around 14.5 billion years. Combined with refined models of stellar evolution, this brought Methuselah's age just under the universe's 13.8 billion year timeline, resolving the paradox. What makes Methuselah so invaluable isn't just its extreme age, it's how it tests the limits of our cosmic dating techniques. Like a watchmaker fine-tuning an antique timepiece, astronomers used this star to calibrate their models of how ancient stars cool and evolve. They discovered that slight adjustments to factors like stellar opacity, how easily light passes through a star's layers, could significantly impact age calculations. Methuselah also revealed unexpected complexities in early star formation. Its unusual oxygen-to-iron ratio suggests it may have been born in a dwarf galaxy that later merged with the Milky Way, making it not just old, but a celestial immigrant carrying secrets from another corner of the early universe. This star's story exemplifies the iterative nature of cosmic detective work. Initial contradictions forced scientists to question their assumptions, leading to more precise measurements and sophisticated models. Today, Methuselah serves as a benchmark for studying other ancient stars, helping astronomers distinguish true primordial relics from slightly younger imposters. Its revised age also validated the cosmic timeline derived from the cosmic microwave background, creating consistency between stellar and universal clocks. Beyond textbooks, Methuselah offers a humbling perspective. When this star first ignited, the universe was a vastly different place. No galaxies as we know them, no planets, just a dark expanse lit by the first generations of massive, short-lived stars. That its light reaches us now, carrying encoded details about that forgotten era, feels like receiving a message in a bottle from the cosmic dawn. Every observation of this stellar elder adds another piece to the puzzle of how our galaxy, and by extension, we came to be. In studying Methuselah, we're not just measuring time, we're touching a living relic that connects us to the universe's first breaths. Galactic fossils aren't just time capsules, they're potential gravestones of civilizations we'll never know. When a star like our Sun dies, becoming a white dwarf, it doesn't just erase the planets that once orbited it. Instead, it preserves their remains in an eerie, almost forensic detail. The atmospheres of these stellar corpses often contain heavy elements like calcium, iron, and even oxygen materials that should have sunk beneath their surfaces eons ago. The only explanation: these white dwarfs are actively consuming the shattered remnants of their own planetary systems. But here's where it gets fascinating: the chemical fingerprints of those ingested worlds might reveal whether life ever existed there, billions of years before Earth formed. Take GD61, a white dwarf located about 150 light-years away. Spectroscopy revealed its atmosphere contains an excess of oxygen alongside rocky materials like magnesium and silicon. Normally, oxygen quickly binds with other elements, so finding it in such abundance suggests this star swallowed a water-rich body, perhaps an exoplanet with oceans deeper than Earth's. Now imagine a similar world, but with something more. If life had emerged there, its biological processes might have altered the planet's chemistry in detectable ways. Photosynthetic life, for instance, tends to enrich atmospheres with specific oxygen isotopes. While the organisms themselves would be long gone, their atomic signatures could persist in the white dwarf's atmosphere like ghostly echoes. This transforms galactic fossils into a new frontier for astrobiology. While most searches for extraterrestrial life focus on contemporary exoplanets, white dwarfs let us investigate life's potential across cosmic epochs. Some of these stellar remnants are over 10 billion years old, meaning their planetary systems had a head start of 5 billion years on Earth. If life arose in even a fraction of those ancient systems, its chemical traces might still linger in the data we collect today. The challenge lies in distinguishing biological signatures from geological ones. A spike in phosphorus or certain carbon molecules could hint at past biology, especially if paired with atmospheric imbalances that resemble Earth's great oxygenation event 2.4 billion years ago. But the implications go deeper. Consider that most stars in the Milky Way will eventually become white dwarfs, including our Sun. In 5 billion years, Earth might be reduced to elemental vapors swirling around a dead star, its biosphere preserved only as isotopic ratios in a stellar atmosphere. This morbid thought experiment reveals a profound truth: galactic fossils don't just expand where we look for life, but when. They force us to confront the possibility that we might be latecomers in a cosmic drama of life and death that's been playing out since the universe's first generations. The next generation of telescopes could turn these speculations into concrete discoveries. The James Webb Space Telescope's infrared capabilities are already analyzing white dwarf atmospheres for complex molecules. Future instruments like the extremely large telescope's Andes spectrograph will hunt for biosignatures with precision down to 1 part in a billion. If they find even a single white dwarf with chemical anomalies suggesting ancient biology, it would rewrite our understanding of life's cosmic timeline. Suddenly, astrobiology wouldn't just be about finding neighbors, it would be about uncovering ancestors, civilizations that thrived and vanished before our solar system even existed. This shifts the fundamental question from "Are we alone?" to "How many times has life arisen?" Galactic fossils offer a humbling perspective that life's story might be far longer and richer than we've dared imagine. They remind us that while individual species and planets are fleeting, the universe has been experimenting with biology's possibilities for nearly its entire existence. In the atmospheres of dead stars, we might not just find traces of extinct life, we might discover how common or how rare our own chapter in that story truly is. Imagine watching the birth of a neutron star unfold in vivid detail. not through a telescope but on a supercomputer screen. This is the power of modern astrophysical simulations, where equations transform into dynamic visualizations of cosmic evolution. Scientists create these virtual universes by encoding the laws of physics into sophisticated software, then letting them run for millions of processor hours to recreate billion-year processes in weeks. One such simulation, called Illustris TNG, models a cube of space 300 million light-years wide, tracking how dark matter, gas, and stars interact from the Big Bang to today. When researchers compare its outputs to actual galaxy surveys, the match is uncanny, proof that these digital laboratories can accurately reverse engineer cosmic history. What makes simulations indispensable is their ability to explore the unobservable. While telescopes capture snapshots of galactic fossils at various life stages, simulations show the continuous transformations between those moments. Take white dwarf crystallization, a process too slow to witness in real time. By programming in quantum mechanical principles governing how carbon atoms arrange under extreme pressure, physicists can watch a virtual white dwarf's core solidify over simulated millennia. The resulting phase diagrams explain why some stellar remnants cool faster than expected, solving mysteries that puzzled astronomers for decades. Similarly, simulations of supernova shockwaves reveal how these explosions distribute heavy elements, showing why certain isotopes cluster in specific regions of the Milky Way. The true magic happens when simulations contradict expectations. A team at the University of California recently modeled globular cluster formation with updated stellar wind parameters, unexpectedly finding that these ancient structures could form in just 50 million years, 10 times faster than previous estimates. This discovery forced a rewrite of how early galaxies assembled their stellar populations. Other surprises come from what-if scenarios. When astrophysicists at Cambridge simulated a universe with slightly stronger dark matter interactions, they produced galaxy shapes that matched peculiar fossils like the ultra-diffuse Dragonfly 44, suggesting invisible forces sculpted its eerie transparency. These virtual time machines also bridge gaps in the fossil record. Consider the puzzling absence of intermediate mass black holes, theoretical stepping stones between stellar and supermassive varieties. Simulations tracking black hole mergers in dense star clusters show how these middling monsters might rapidly grow or be ejected before we can spot them. Another enigma, the diversity of planetary systems around white dwarfs, finds clarity in simulations incorporating rogue planet encounters. By watching thousands of digital planetary systems destabilize post-red giant phase, researchers see how some worlds survive while others spiral into their stars, explaining the varied chemical signatures observed. As computing power grows, so does simulation fidelity. Next-generation models will incorporate feedback from gravitational wave detectors and neutrino observatories, adding multidimensional physics to the cosmic recipe. Projects like the Cosmic Web Reconstruction aim to simulate our local universe down to individual galaxy filaments, using real observational data as starting points. The ultimate goal, a complete digital twin of the Milky Way where every known white dwarf, neutron star, and stellar stream evolves according to measured initial conditions. A virtual fossil collection where scientists can rewind, pause, and test theories at will. Yet for all their sophistication, simulations remain humbling approximations. The universe operates with perfect physics. Our models use clever shortcuts to fit within computing constraints. This limitation sparks creativity. When a simulation consistently produces neutron stars slightly less dense than observed, physicists know to revisit their equations of state for nuclear matter. Every discrepancy between digital and real fossils becomes an opportunity to refine our understanding. what emerges is a symbiotic relationship between silicon and starlight. Telescopes provide the raw material chemical abundances, orbital dynamics, radiation patterns, while simulations animate that data into coherent narratives. Together, they form a time-traveling detective team, piecing together the universe's biography from fragmentary evidence. The next time you see a visualization of colliding galaxies or crystallizing white dwarfs, remember, you're not just watching a pretty animation, but a rigorous scientific experiment unfolding in the most advanced time machine humanity has ever built. One of the most persistent myths about galactic fossils is that they're somehow still alive, that white dwarfs are simply aging stars, or that pulsars are actively feeding like black holes. In reality, these objects are stellar remnants, the final evolutionary stages of stars that have exhausted their nuclear fuel. A white dwarf isn't a dimming star, it's the exposed core of a dead one, slowly radiating away its residual heat over billions of years. Similarly, pulsars aren't powering their rapid spins with fresh energy. They're cosmic flywheels, conserving angular momentum from their progenitor stars' collapse. This distinction matters because it shapes how we interpret their role as timekeepers. A living star's behavior changes as it burns fuel, but a galactic fossil's evolution follows predictable physical processes like cooling or spin down, making them far more reliable chronometers. Another widespread misunderstanding centers on how these objects actually measure time. It's easy to imagine a pulsar's regular pulses as some kind of cosmic grandfather clock, ticking away the seconds. But their real value lies in their astonishing consistency over millennia, not their fleeting human-scale rhythms. A pulsar's spin might slow by mere microseconds per century, making it a natural timepiece far more stable than any atomic clock we've built. Likewise, a white dwarf's surface temperature doesn't drop like a cooling cup of coffee. It follows precise thermodynamic curves dictated by quantum physics in its crystallizing core. These processes operate on timescales that defy everyday intuition, which is why analogies comparing them to earthly clocks often fall short. The confusion extends to how we perceive distance and age in these relics. When we observe a globular cluster like Omega Centauri, its brilliant glow might suggest it's a young structure, when in fact its stars are among the oldest in the galaxy. Similarly, the vivid remnants of a supernova like Cassiopeia appear dynamic and fresh, but their light has traveled centuries to reach us. The explosion itself occurred long before telescopes existed. This disconnect between appearance and reality underscores why galactic fossils require contextual understanding. Their light is a delayed message, and their present state is often a palimpsest of layered histories waiting to be decoded. Perhaps the most detrimental misconception is that studying these objects is purely academic with no practical relevance. In truth, galactic fossils are testing grounds for fundamental physics. The intense gravity on a neutron star's surface probes general relativity in ways no Earth lab can match. The crystalline cores of aged white dwarfs reveal how matter behaves under pressures 1,000,000 times greater than our planet's core. Even the cosmic microwave background, often dismissed as mere static, contains clues about the universe's birth that could rewrite our understanding of reality. Dismissing these fossils as distant curiosities misses their profound role in expanding human knowledge. Demystifying these concepts does more than correct factual errors. It transforms how people engage with the cosmos. When someone learns that the carbon in their body came from stars that died billions of years ago, or that pulsar timing might one day help navigate interstellar travel, astrophysics shifts from abstraction to personal connection. Science communicators bridge this gap by replacing jargon with vivid analogies, comparing white dwarf crystallization to water freezing in slow motion. or describing stellar streams as celestial breadcrumbs leading back to ancient galactic collisions. The goal isn't to simplify the universe's complexity, but to make its wonders accessible without dilution. This educational mission has never been more vital. In an era where misinformation spreads rapidly, equipping the public with accurate cosmic literacy fosters a society that values evidence, critical thinking, and the humility that comes from understanding our place in deep time. When we look at a Hubble image of a globular cluster or an X-ray map of a supernova remnant, we're not just seeing pretty pictures, we're witnessing pages of a history book written in starlight. Ensuring those pages are read correctly is how awe becomes insight, and how casual stargazers become thoughtful explorers of the universe's grand narrative. As we reach out to study these ancient celestial relics, we face ethical dilemmas no less complex than those confronting archaeologists on Earth. The atmospheres of white dwarfs, for instance, act as pristine chemical archives, but a single spacecraft passing too close could introduce contaminants that distort their composition for centuries. Imagine a future mission to collect samples from a crystallizing white dwarf's debris disk, only to have its exhaust plumes deposit modern Earth elements onto surfaces that have remained untouched for billions of years. The isotopes we study to date cosmic events could become hopelessly muddled, like smudging ink on a fragile medieval manuscript. This isn't hypothetical. NASA's upcoming Louvre Space Telescope will have protocols requiring its instruments to maintain strict orbital boundaries around stellar remnants, treating them with the same caution as sterilized Mars rovers handling potential biosignatures. The challenge extends beyond contamination. Some galactic fossils, like the delicate stellar streams wrapping around the Milky Way, are held together by gravitational threads so tenuous that even minor disturbances could alter their structure. Probes sent to study these formations must calculate their trajectories to avoid gravitational wakes that might disperse stars from their shared orbits, an interstellar version of museum visitors being asked not to touch priceless artifacts. There's precedent for such caution. When the European Space Agency's Gaia spacecraft mapped stellar motions, its operational guidelines included minimizing thruster firings near known streams to prevent artificial perturbations. Future missions might need to implement herding protocols, where swarms of microsatellites work in concert to study these structures without any single probe coming close enough to disrupt them. Ethical cosmic archaeology also means acknowledging indigenous perspectives on the night sky. Many cultures view specific stars or nebulae as sacred narrative landmarks. The Jukirpa dreaming stories of Australia's Aboriginal peoples, for example, intricately connect celestial patterns to terrestrial landscapes. As we analyze these astronomical features through a scientific lens, we must engage with traditional knowledge holders to ensure research respects cultural heritage. The Large Synoptic Survey Telescope, now named the Vera Rubin Observatory after consultation with Native American communities, set a precedent by establishing protocols for culturally sensitive observation of regions like the celestial path known as the Milky Way's dark emu in Aboriginal astronomy. Perhaps the most profound ethical question is intergenerational equity. The radioactive decay clocks in ancient stars will keep ticking for billions more years, while our current observational technologies are still in their infancy. Mining white dwarfs for rare elements or altering neutron star orbits for gravitational wave experiments might yield short-term gains, but could irrevocably destroy cosmic evidence future civilizations with better tools might have decoded. The Outer Space Treaty of 1967 provides some framework, but new guidelines specifically protecting stellar fossils are now being drafted by the International Astronomical Union's working groups. These propose designating certain relics like the oldest pulsars or primordial gas clouds as cosmic heritage sites, with observation-only restrictions akin to UNESCO protection of Earth's cultural treasures. This ethical framework doesn't stifle discovery, it enriches it. By treating galactic fossils as a shared legacy rather than exploitable resources, we honor the same principle that guides museum collections, preserving context so future generations can ask questions we haven't yet imagined. The dust grains in a dying star's debris disk might hold clues to planetary formation that seem irrelevant today, but become crucial centuries hence when humanity encounters exoplanets with similar compositions. Our responsibility isn't just to the science of now, but to the scientists of tomorrow who will inherit both our data and our mistakes. In this vast universe where time is measured in stellar lifetimes, ethical stewardship is how we ensure the cosmic story remains legible long after our own chapter has ended. Galactic fossils aren't just scientific curiosities, they're powerful storytellers with the ability to ignite young imaginations like nothing else. Picture a group of middle schoolers gazing at a Hubble image of the Crab Nebula, their eyes widening as they realize they're seeing the shattered remains of a star that exploded before the pyramids were built. That moment of awe is where lifelong passions are born. Educators and outreach programs have tapped into this magic, using these cosmic relics as springboards to teach far more than astronomy. When students analyze real data from pulsars or track the cooling curves of white dwarfs, they're not just memorizing facts, they're learning how to think like scientists, asking questions about the universe and interpreting evidence to find answers. Take the Pulsar Explorers program at the Green Bank Observatory, where high school students use radio telescopes to time the pulses of neutron stars. These teens aren't just pressing buttons, they're collecting data that contributes to actual gravitational wave research, seeing firsthand how their measurements help test Einstein's theories. Programs like this demystify the scientific process, showing that discovery isn't about having all the answers, but about curiosity and persistence. A student might start by wondering why a particular pulsar's rhythm seems irregular, only to learn they've stumbled upon evidence of an orbiting planet or a glitch in the star's superdense crust. Suddenly, abstract physics concepts become tangible puzzles waiting to be solved. What makes galactic fossils such effective teaching tools is their ability to bridge scales, from the quantum behavior of particles in a neutron star to the mind-bending vastness of cosmic time. A simple activity comparing the sizes of different stellar remnants can lead to profound discussions about density, gravity, and the life cycles of stars. The Sloan Digital Sky Survey's Galactic Archaeology initiative lets students explore real star maps, identifying ancient stellar streams that reveal our galaxy's cannibalistic past. These experiences stick because they're not just lessons, they're adventures, with students as the explorers uncovering secrets written in starlight. The impact goes beyond classrooms. Public Planetarium shows featuring Supernova Remnants or interactive museum exhibits about white dwarf chemistry make these concepts accessible to all ages. The Chandra X-ray Observatory's Cosmic Fossils curriculum has reached thousands of underserved students, proving you don't need a fancy lab to study the universe, just curiosity and the right guidance. Even social media plays a role, with astronomers using platforms like TikTok to explain how the iron in our blood came from long-dead stars, connecting everyday life to cosmic processes billions of years in the making. Perhaps most importantly, these initiatives show science as a human endeavor. When students learn that Jocelyn Bell Burnell discovered pulsars as a graduate student, or that Vera Rubin's work on galaxy rotation curves revealed dark matter despite initial skepticism, They see that scientific breakthroughs aren't just for geniuses, they're within reach of anyone willing to observe carefully and think critically. Galactic fossils become more than distant objects. They're milestones in humanity's ongoing quest to understand our place in the cosmos, inviting the next generation to add their own chapters to that story. The true measure of success isn't how many students become professional astronomers, it's how many retain that sense of wonder when looking at the night sky, understanding that every star has a story waiting to be deciphered. Some may become engineers inspired by pulsar navigation systems, or writers captivated by the poetry of stellar life cycles. Others might bring scientific thinking to entirely different fields, approaching problems with the same curiosity they once applied to decoding the universe's oldest relics. In the end, galactic fossils don't just teach us about the past, they help shape the minds that will explore the future. The data streaming from galactic fossils, numbers on a screen, wavelengths on a graph, transforms into something transcendent when artists lend their vision to the cosmos. Take the iconic Pillars of Creation image from the Hubble Space Telescope. What began as raw spectroscopic data became a swirling nebula of color, its towering columns of gas and dust rendered in hues the human eye could never perceive. This isn't mere decoration, it's translation. Scientists provide the coordinates of a supernova remnant's shockwaves, and digital painters like J.P. Metzevanio use volumetric modeling to reconstruct its three-dimensional structure, layer by layer. The result, a pulsar's magnetic field becomes a dynamic sculpture of twisting light, and the chaotic debris around a white dwarf resolves into a delicate watercolor of planetary demise. These collaborations between labs and studios do more than beautify, they recontextualize. When NASA Chandra X-ray Observatory partnered with illustrator Dana Berry, her interpretations of neutron star collisions didn't just illustrate press releases, they revealed nuances in the data. One painting highlighted how opposing jets of particles from a merging binary system created symmetrical arcs, a detail buried in spreadsheets that leaped out when visualized. Artists often spot patterns scientists overlook, their fresh eyes turning abstract data points into cohesive narratives. The famous Golden Record aboard Voyager epitomizes this synergy. Astronomer Carl Sagan worked with musicians and artists to encode humanity's essence into sounds and images, proving creativity and science share a common language when grappling with the infinite. What makes these artistic interpretations so vital is their ability to humanize cosmic timescales. A graph showing a white dwarf's cooling curve over billions of years is clinically precise, but a time-lapse animation of its crystallization, with each frame representing millennia, makes the unfathomable feel visceral. Digital installations like Rafik Anadol's Machine Hallucinations use AI to transform archival telescope images into immersive experiences, letting viewers physically walk through evolving supernova remnants. Suddenly, the death of a star isn't a distant event. It's a sensory journey where light and sound embody the passage of deep time. This fusion of disciplines also reshapes how we communicate discovery. When the Event Horizon Telescope captured the first image of a black hole's shadow, the faint radio wave data required algorithmic enhancement to become recognizable. But it was the accompanying artist's conception, a fiery ring warping spacetime, that seared the achievement into public consciousness. Similarly, children's books like The Stuff Between the Stars use whimsical illustrations to explain dark matter's role in galactic evolution, planting seeds of curiosity that technical papers couldn't reach. Perhaps the most profound impact lies in art's capacity to evoke wonder where equations elicit analysis. A pulsar's precise radio pulses might inspire a physicist to calculate its spin-down rate, but composer George Crumb's Macrocosmos translates those rhythms into haunting piano sequences, making the neutron star's heartbeat audible. At planetariums worldwide, shows like Dark Universe blend scientific narration with surreal visuals, transforming cosmic microwave background maps into a shimmering tapestry of the Big Bang's afterglow. These experiences don't replace rigor, they complement it, proving that understanding the universe requires both our analytical minds and our capacity for awe. The legacy of this synergy is everywhere, from the stained glass windows of cathedrals depicting medieval supernova to modern sci-fi films consulting astrophysicists for accuracy. Humanity has always used art to process the cosmos. Today's tools simply allow deeper collaboration where a painter's brushstroke might highlight a previously unnoticed filament in a galactic fossil, or a musician's interpretation of stellar vibrations reveals hidden harmonics in the data. In the end, these creative partnerships remind us that galactic fossils aren't just subjects of study. They're part of our cultural heritage, their stories waiting to be told through both numbers and narratives. Galactic fossils have long captivated storytellers, their ancient whispers echoing through science fiction and cinema alike. Consider the pulsar in Arthur C. Clarke's The Songs of Distant Earth, depicted with startling accuracy as both a timekeeper and navigational beacon for interstellar travelers. This portrayal wasn't just poetic license. Clarke consulted astrophysicists to ensure the spinning neutron star's physics aligned with reality. The result, a narrative device that educated millions about these cosmic lighthouses while advancing the plot. Hollywood blockbusters take similar care. When Interstellar visualized Gargantua's accretion disk, the fiery swirls weren't random special effects, but mathematically precise renderings based on Kip Thorne's equations, showing how even black holes leave gravitational fossils in their wake. What makes these pop culture appearances so powerful is their ability to humanize cosmic timescales. The white dwarf in the Doctor Who episode, The Rings of Akhenaten, becomes more than a dying star. It's the glowing heart of an alien bazaar, its gradual cooling mirroring the story's themes of mortality and legacy. Video games like Mass Effect leverage real astronomy too, with the Citadel space station orbiting a neutron star, its deadly radiation belts forcing ships to navigate carefully, a gameplay mechanic rooted in actual pulsar hazards. These creative choices do more than dazzle audiences. They embed scientific concepts into collective consciousness, making terms like supernova remnant feel familiar rather than esoteric. Yet pop culture's greatest service might be revealing our societal fascinations, the recurring motif of ancient alien civilizations leaving messages in stellar remnants from the monolith in 2001. A Space Odyssey to the pulsar map in Contact speaks to humanity's yearning to find meaning in the cosmos. When films depict archaeologists studying extraterrestrial ruins on dead planets, they're mirroring real scientists analyzing planetary debris in white dwarf atmospheres. This parallel between fiction and research highlights a profound truth. We're instinctively drawn to cosmic relics as both scientific subjects and mythological symbols. The educational impact is undeniable. After Star Trek featured a binary neutron star system, NASA reported increased public interest in gravitational wave astronomy. Similarly, the accurate portrayal of time dilation near Gargantua sparked classroom discussions about relativity. Even errors have value. When a movie misrepresents a supernova's timescale, it creates teachable moments about how these explosions actually unfold over weeks rather than seconds. The best sci-fi walks a tightrope, balancing spectacle with enough realism to inspire rather than mislead. What emerges is a virtuous cycle. Scientific discoveries inspire artists, whose works then ignite public passion for astronomy. The dark matter halos in the dark crystal parallel actual galaxy formation theories, while the crystalline core of Superman's homeworld Krypton echoes real hypotheses about diamond-rich white dwarfs. These creative interpretations don't just reflect current science, they anticipate future research directions, with storytellers often intuiting concepts that later gain empirical support. When audiences encounter these ideas in labs after seeing them in theaters, the universe feels less like a collection of data points and more like an ongoing story we're all helping to write. This cultural alchemy transforms galactic fossils from academic curiosities into shared touchstones. Whether it's a child building a pulsar model after seeing one in a cartoon or a novelist crafting plot twists around real exoplanet discoveries, these cross-pollinations between science and art ensure cosmic history remains vibrant and accessible. The next time you spot a supernova remnant in a video game or hear a white dwarf mentioned in a song lyric, remember, you're witnessing humanity's oldest tradition, turning celestial wonders into stories that bridge the vastness of space and time. Standing beneath a sky strewn with galactic fossils, we're confronted with a paradox. These ancient relics make us feel impossibly small yet profoundly connected. Each white dwarf's cooling glow, every pulsar's rhythmic beat, carries echoes of events older than Earth itself, reminding us that our lives unfold in the briefest sliver of cosmic time. Yet in that humility lies an unexpected gift, the realization that we're woven into the same narrative that forged these celestial timekeepers. The carbon in our cells, the iron in our blood, these elements were smelted in stellar furnaces and scattered across space by explosions that occurred before the sun ignited. We're not just observers of the universe's history, we're its living continuation. Stardust evolved to consciousness. This perspective shifts how we measure what matters. Human achievements that loom large in textbooks, wars, empires, artistic movements span mere heartbeats against the billion-year rhythms of galactic fossils. A neutron star's spin has outlasted every civilization that ever rose and fell on Earth, and will persist long after our cities have crumbled to dust. Yet, rather than diminishing our significance, this vast timescale reveals something extraordinary. Against all cosmic odds, we've emerged at just the right moment to piece together this story. The universe spent billions of years preparing the stage, cooling, structuring, forging heavy elements so that now, in this fleeting window, it can contemplate itself through our eyes. Galactic fossils also challenge our instinct to see time as linear and finite. A supernova remnant isn't just a relic of destruction, it's a nursery where shockwaves compress gas into new stars. The white dwarf crystallizing into a cosmic diamond will one day be recycled into future planetary systems. These objects whisper that endings are illusions. The universe operates in cycles where every death seeds new beginnings. This cyclical perspective can reframe personal struggles, helping us see setbacks not as finality but as transformations, much like the violent stellar deaths that ultimately made life possible. Perhaps most powerfully, these ancient messengers dissolve the boundary between us and the cosmos. When we study the uranium-thorium ratios in a 13-billion-year-old star, we're not just analyzing data, we're communing with a witness to the universe's infancy. The light from the Crab Nebula that reaches our telescopes tonight began its journey when Vikings were exploring the North Atlantic, connecting medieval explorers to modern scientists across a millennium. In an age of digital immediacy, galactic fossils teach patience, inviting us to contemplate timescales that humble our hurried existence. They also offer solace in impermanence. Just as we now decode the stories of long-dead stars, future civilizations, human or otherwise, might study the Voyager probes or radio signals as relics of our era. Our artifacts could become galactic fossils too, carrying fragments of our culture into the deep future. This interdependence across time fosters a sense of responsibility, not just to preserve knowledge, but to ensure the story we add to the cosmic record is one worth remembering. When we look up at these ancient celestial storytellers, we're reminded that we belong to something far grander than our daily concerns, a universe that remembers, evolves, and continues its magnificent unfolding. Galactic fossils are not merely distant objects to catalogue. They are the universe's memory, etched in stardust and radiation. Every white dwarf's slow crystallization, each pulsar's steady beat, and even the faint whisper of the cosmic microwave background form a collective chronicle of existence. These relics are more than scientific specimens. They're the universe reflecting on its own history, preserving moments that would otherwise vanish into the void. When we study them, we're not just analyzing data. We're reading a story that began billions of years before Earth formed, one where supernova forged the elements of life and gravitational waves carried echoes of collisions older than time itself. Consider the profound duality of these cosmic artifacts. A white dwarf's cooling curve marks the end of a star's life, yet its chemical makeup reveals the birth of planets that once orbited it. The cosmic microwave background captures the universe's first light, but its subtle fluctuations also hint at the galaxies and voids that would one day emerge. Even dark matter, invisible and enigmatic, leaves behind gravitational fingerprints that let us reconstruct the cosmos's structure across eons. These fossils don't just record events, they connect them, showing how the universe transforms destruction into creation, chaos into order. What makes this exploration so deeply human is its universality. You don't need a telescope to feel the weight of these discoveries. The iron in your blood, the calcium in your bones, these elements were born in the hearts of long-dead stars, scattered across space by explosions that lit up the primordial darkness. Every atom in your body carries a lineage stretching back to the first moments of time, making you a living testament to the very processes we observe in these galactic fossils. They remind us that we're not separate from the cosmos. We're its conscious embodiment, capable of turning starlight into understanding. The journey doesn't end with what we've uncovered so far. Each answer gleaned from these relics sparks new questions, pushing the boundaries of our knowledge. Could pulsars hold clues to the nature of spacetime itself? Might the isotopic patterns in white dwarfs reveal lost planetary systems that once harbored life? As technology advances, so too will our ability to listen to these ancient storytellers, peeling back layers of history we've only begun to imagine. The universe has been patient in revealing its secrets, and we're just learning how to listen. So when you gaze at the night sky, remember, you're not just looking at points of light. You're seeing a dynamic, ever-evolving archive where every flicker and shadow carries meaning. Galactic fossils invite us to ponder our place in a timeline far grander than our own, not to diminish our significance, but to celebrate our role in the universe's unfolding narrative. They teach us that curiosity is our greatest compass, guiding us through the vastness of space and time. Whether you're an astronomer, a stargazer, or simply someone who pauses to wonder, these celestial relics whisper the same truth. The cosmos remembers, and so